Okay, so we're going to start talking about, with sort of this background now, we'll start talking about wavelet packets. And what's fascinating is that Walsh actually did it, but not this exact way, back in 1923. And he more or less did it the same way one thinks of structurally today. He knew about the Haar's thesis in 1909, and he made these orthonormal bases, which are called Walsh functions. The update of that story is the following. We have multi-resolution analysis theory, and we have lots of special cases. One special case of multi-resolution analysis is the Haar wavelet. It turns out that when you do the magic abracadabra on the Haar system in the context of multi-resolution analysis, you get the Walshes. Because of the generality of multi-resolution analysis, if you start off with any multi-resolution analysis that's going to give you a wavelet, then you do this abracadabra, and you're going to get wavelet packets corresponding to that original wavelet. So we've got a machine now that generalizes the Haar-Walsh function relationship. So the Haar-Walsh function relationship goes back a long time, 85 years, and it says in modern terminology, you've got an orthonormal basis in terms of Haars, and then you can make these Walsh system, which is another orthonormal basis, but has a lot of other properties. With multi-resolution analysis, you take any wavelet that comes from multi-resolution analysis, then you make something called wavelet packets, which will give you a lot more orthonormal bases, and that's the exact analog that the Walshes have to the Haars. Was that more or less clear? No? To anyone? To no one? To me, John? Well, no, you gobbled it, I think. Okay. Okay, well, let's just write it down. Sorry.
What is the relation of the Walshes to the Haars?
I'm going to show you either later today or technically, or the beginning next time, but if you think of starting off with phi as the characteristic function of 0, 1 on the real line, and generate V0, then you build up this tree, and in particular you get a wavelet in W0, which turns out to be this function here when you do the MRA theorem.
Mm-hmm.
And you get a wavelet orthonormal basis, a Haar wavelet orthonormal basis, L2 of R. The Walshes, if you just keep that structure with the Walsh number, with the Haar functions in here, then there's a natural way of filling in this whole tree. And those are the Walsh functions. At least you can think, I'll be more precise, but it allows you to fill in the tree. And the point is we can do that with any, we can do that with any wavelet system now, and we have a method, I'm going to show you a method of filling in the tree. And those will be the analog for Walsh functions. Okay? Okay, let me just stop talking. So from the MRA algorithm, the MRA algorithm, we're going to have that phi of t is equal to the sum of h0 of n, and then phi 1 n of t, and that's going to converge, that belongs to V1, and that converges in L2. And similarly, the wavelet that we get that's in W0, that's going to be equal to the sum of H1 of n, phi 1 n of t, and that's also going to be in V1, and that converges in L2. Bye-bye. Okay? That's just doing this by the scaling relationships. Well, when we do the, as we know, when we do the Fourier transforms of these guys, we get that square root of 2 phi hat of 2 gamma is equal to H0 of gamma phi hat of gamma, and we get the square root of 2 of psi hat of 2 gamma is equal to H1 of gamma phi hat of gamma, where H0 is the guy that comes from the multi-resolution analysis, and H1 is the guy that comes from our construction in the MRA thing. Okay? That I actually wrote earlier. All right. Okay. Now, we want to look at this tree, and the only thing we know about this tree right now is how to do V minus 1, W minus 1, etc. We don't know these. But let's be inspired by what we see here. So let's look at that. So let's look at V minus 1 and write down some things we know about it. What we have is, we have that, we're going to look at phi minus 1 n of t, and that's equal to 1 over the square root of 2 phi, just by definition of course, of t over 2 minus n, and that has as its Fourier transform e minus 2n of gamma, square root of 2, and then phi hat of 2 gamma, where e minus r of gamma is equal to e to the 2 pi I minus 2 pi I r. Okay? And of course, these guys here form an orthonormal basis of V minus 1. And the other thing we know is what I wrote over here in the left border. Let me write it here again just because I want to be a little systematic. We have the phi hat of 2 gamma is equal to phi hat of gamma H0 of gamma. Well, what happens when we do W1? Well, when we do W1, minus 1 rather, we have that psi minus 1 n of t is equal to 1 over the square root of 2 psi of t over 2 minus n. And that has as its Fourier transform e minus 2n of gamma square root of 2, and then psi hat of 2 gamma. And then psi hat of 2 gamma times the square root of 2 is equal to phi hat of gamma H1 of gamma. So in some sense, what I've just done is I've written down almost everything we know about these two guys. Now, let's do a splitting of V minus 1. What does that mean? Well, to do a splitting of v minus 1, I'm going to get the following. Excuse me. So split v minus 1. And we have that 1 over the square root of 2 quantity squared, phi of t over 2 squared minus m. That has, and also 1 over the square root of 2 squared psi of t over 2 squared minus m. Okay? So I'm making this orthonormal basis of v minus 1 by looking at these guys here, which are in v minus 2, and these guys here, which are in w minus 2. So this is how, at the beginning of class today, I wrote down a new orthonormal basis for v minus 1. Now I'm actually going to use that idea. And so, if I write down the same thing for v minus 2 that I did here for v minus 1, what I have is I've got v minus 2, and I have then phi minus 2n of t, which is just equal to 1 over the square root of 2 quantity squared phi of t over 4 minus n. And that has as its Fourier transform e minus 4n of gamma square root of 2 quantity squared phi hat of 4 gamma. And what's phi hat of 4 gamma? Well, phi hat of 4 gamma is equal to, let me just put the square root of 2 squared in front of it. Is equal to phi hat of gamma, phi h0 of gamma, h0 of 2 gamma. And that is the key observation for running the whole way. Because this guy here is equal to, if I write down what the phi hat of 4 gamma is, basically I have that, in fact, phi hat square root of 2 squared phi hat of 4 gamma is equal to, well, I've got the square root of 2, and then phi hat of 2 gamma, and then h0 of 2 gamma, right? Because that's my original, that's the formula I have from over here, where gamma is equal to 2 gamma over there. And this then, phi hat of 2 gamma though, is just going to be that other square root of 2. And so what I get is this is equal to phi hat of gamma, h0 of gamma, h0 of 2 gamma. So I have this fact here. Now having that fact there gives us a little bit of courage, and we go look at w minus 2. Well, w minus 2, if I write the splitting that way, I have that psi minus 1 n of t, oops, psi minus 2, n t. I don't have to write it all out since I've been burning a lot of chalk here. So just, so that's equal to psi 1 over the square root of 2 squared of psi of t over 4 minus n. But its Fourier transform is e minus 4 n of gamma square root of 2 quantity squared psi hat of 4 gamma. Well, what is psi hat of 4 gamma? Psi hat of 4 gamma, oops, psi hat of 4 gamma, if I multiply times the square root of 2 squared, is equal to d hat of gamma h0 of gamma h1 of 2 gamma. Now the h's, of course, are one periodic functions. So this is truly the moment of truth. Because, yes.
So over here, this is supposed to, in the last line of the chalkboard, that should be H1 or 2 gamma?
No, this is correct.
That's
I'm,
correct.
I'm dealing with fees here.
Oh, I see, I see.
And here, because I have psi's, basically if I do the psi hat of 4 gamma, I go back to what this looked like. But I replace the gamma by 2 gamma, so I have psi hat of 4 gamma, I pick up that h1 and 2 gamma. Okay, so given that situation, let's talk about one little technique we need, which is called bit reversal. And bit reversal plays a big role, for those of you who play with the fast Fourier transform, in the fast Fourier transform, and it plays a big role in lots of things. And when I first studied it, I made the mistake of studying it out of a very, very high-powered algebraic book, and I didn't understand anything. So that was good news, because I finally figured it out, but not from that book. In any case,
Was it a good book?
huh?
Was it a good book?
I didn't understand it well enough to know. So, I wasn't ready for it at the time. Of course, that's my excuse until because they don't like my classes. I say, well, they probably weren't ready for me at that time. But let's, in order to clinch the deal for filling out the tree, like the Joyce Kilmer lecture, we're going to, we need to say something about bit reversal. So let's let n equals 2 to the I. And let's look at level R equals 1. By the way, in my book on harmonic analysis, I've written about this sort of extensively there, and how it works in the fast Fourier transform. Okay, so just by definition, the bit reversal ordering of the set 0, 1 is the ordered 2 to the 1 tuple 0, 1 by fiat. Okay? Why not? Now, level R equals 2. The bit reversal ordering the set 0, 1, 2, and 3. And by the way, I'm looking at a tree now, just as this is something you keep in the back of your mind, where I'm here, and then I've got a tree where I'm really looking at 0 and 1. Then I'm looking at 0, 1, 2, and 3. And I'm looking at 0, 1, 2, 3, 4, 5, 6, 7. Now, don't tell anyone this is what we were looking at, right? But that's what we're thinking of as we proceed here. The bit reversal ordering 0, 1, 2, 3 is the ordered 2 to the 2 tuple zero, 2, 1, and 3.
That's just like the elements of the adding expansion every month.
Yeah, that's exactly what we're doing, okay? But just in case everyone didn't understand that, I'm going to do it the current rate I'm doing. Inductively, at level R equals M, suppose the set zero, 1, 2 up to 2 to the M minus 1. And let's call this number 2 to the M cap M for a moment. So suppose that set has the bit reversal ordering B0, B1, all the way up to B sub M minus 1. Then, by definition, at level M plus 1, the bit reversal ordering of, what is our set now? It's got twice as many elements, so it's got, we're going 0, 1, 2, 3, all the way up to 2 to the M plus 1 minus 1, because this is just 2 times cap M, is, and here's the formula, it's going to be the tuple that's 2 B0, 2 B1, oh, to B1, dot, 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 up to 2 B sub M minus 1. And then we're going to add to those guys 2 B0 plus 1, 2 B1 plus 1, up to 2 B M minus 1 plus 1. And of course, in the case that I wrote down here, That's exactly what it is. Because I just have the previous case is 0, 1, so I multiply that by 2, and I get 0. I multiply that by 2, and I get 2. And then I multiply that times 0, and I add 1 to it, and I multiply that times 2, and I add 1 to it. So that's it. But now, to clinch it, we have to do what Tom said. And so, just so I have the formula handy, when we so let epsilon j equals 0 or 1. Oops. And the binary expansion of n in the set 0, 1, all the way up to 2 to the r minus 1, because if I'm at level r, my tree has 2 to the r elements in it. Right? The binary expansion of that n is n equals the sum j equals 1 to n, excuse me, to r, of epsilon j 2 to the j minus 1, for some collection of epsilon j's equals 0 or 1. Okay. Well, with that in mind now, I'm sorry? I didn't hear what you said, Tom. Float them upside down. Oh, flip them upside down. I'm not sure what you mean by that.
This just made that one bigger. That's the same.
Oh, right, yeah. Yeah, that's true. I don't have to do that right now. I'm just going to write down some trees now. I'm going to grow me a tree. A big tree that has figs on it. Okay, so suppose I'm at level 0. That's going to be my level, and I've got one element there. And then I'm going to have another tree, and I'm at level 1, and I'm going to have 0 element and the, still at level 1, second element. And then I'm going to have another tree coming out of here, and here, and here, and here. I'm at level 2, so I've got these x2s. And if I just write down the bit reversal of the set 0, 1, 2, 3, we've already calculated that over there. It's 0, 2, 1, and 3, right? And so that means that if I write out its binary expansion, those numbers there, but I don't worry about the whole expansion, I just worry about the coefficients. And the coefficients for 0, the epsilons, are 0, 0. The coefficients here are 0, 1. The coefficients here are 1, 0. And then the coefficients here are 1 and 1. So zeros and ones play a very big role in our life. It's, whether it's for coding theory or stuff like this, or lots of. And so, if we start off, if we just wanted to build a tree, this gives us a nice way of ordering. And in general, let's write down something a little more generic. general, at level r minus 1, the space x r of epsilon 1, epsilon 2, up to epsilon r minus 1. We use suggestive language, but nothing suggestive in any bad way. Is the this is r minus 1 here, right? Is the single parent of two trees, namely of xr, we're at the r level now, and all I have here is I've got epsilon 1, epsilon 2, up to epsilon r minus 1 with a 0. This is exactly, I mean, the bit reversal plays a, a really good role. And xr of epsilon 1, epsilon 2, epsilon r minus 1, and 1. So those are the two. If I pick any tree in my infinite tree, for example, this one, all I've done here is add 0 and 1. Add 0 and 1. Make the forest bigger. Well, now, that gives us a way of completing a multi-resolution analysis tree. I mean, this thing with trees is rather general. But if I have a multi-resolution analysis tree, and I've got formulas like this, it is begging for combining them. And that's the wavelet. So let's combine them. Okay, so I can erase this board. Okay, I think this is pretty interesting stuff. I hope some of you really go into some detail with this. And for those of you who are doing anything, and I know some of you have jobs that are related to this, this is a nice project to get involved with. Okay. So, here we are. We're going to let V0 be equal to x0, 0, the top tree. And then at level 1, we're going to have that x1, 0 is going to be equal to v minus 1, and x1, 1 is going to be equal to w minus 1. So I can make my tree okay so far, where I have x0, 0 equals v0, and then I come down and I have x1, 0, which is v minus 1, and x1, 1, which is w minus 1. Right? And then we have at level 2, we have that x2, 0, 0 denotes v minus 2, and x2, 0, 1 denotes w minus 2. That is to say, I've got this and this. And I've got x2, W minus 1, minus 2. And this is V minus 2. And so now we have a genuine way of filling in the tree, because basically, if you recall, for example, I've got these zeros here. That 0 and 0 is going to correspond to that 0 and 0. On this board here, I had a 0 and 1, and that corresponds to this 0 and 1. That was W minus 2. And now I'm just switching. I mean, this is a fantastic idea, isn't it? And now I can just switch for the other two, according to the bit reversal. So I'm telling you something interesting tonight. We may not be covering much as far as many pages. This is quite interesting. And so what that means is we want to finish off. We've got two more tree elements here, right? We've got x2, and then the element is 1, 0. And we've got x2, and the element is 1, 1. So what are these guys? Well, we define, let's do the 1, 0. Define theta 1, 0 and theta 1, 1 by the formulas square root of 2 quantity squared theta 1, 0 hat of 2 squared gamma is equal to phi hat of gamma times these trigonometric series. Now I'm just going to have h1 of gamma and h0 of 2 gamma. I mean, that's the baby. If you're with me, if you're not with me, doesn't mean you're against me, but I'm being an optimist, I'm going to assume that, you know, I guess. But go back and go through this stuff, because it's really sort of fascinating. And then we define omega 1, 1 by squared theta 1, 1 hat of 2 squared gamma is equal to phi hat of gamma h1 of gamma h1 of 2 gamma. And in that case, what, I mean, I'm proceeding formally, but I've got a real formula to follow now. Then what are the trees then? What functions are the trees? Well, the functions of trees are the following. By the way, it took me a long time to figure this out. I don't think you see this sort of detail anyplace, but in any case. X, 1, 0, 2, that tree is the closed linear span of 1 over the square root of 2 quantity squared of theta 1, 0. After all, this is square root of 2 squared, so when I take the inverse transform, the scaling goes the other way. So it's theta 1, 0, and then t over 2 squared minus n, where n is in z. So that's the space. And then similarly for the 1, 1 case, we have that x 1, 1 squared is the closed span, and now I'm just going to put the 1 over the square root of 2 squared theta 1, 1, and then t over 2 squared minus n, where n points to z. And just as an exercise, in fact, maybe this should be mandatory, because I like to make sure people do a little bit of this. Exercise. I mean, this is another one of those easy ones that several of you would say, well, it's not obvious, but sometimes good to put pencil to paper. Prove that this guy here, let me call it 1, 0, and this guy here, 1, 1. Prove these sets, 1, 0, and 1, 1, are orthonormal bases for x, 1, 0, 2, the upper one is the level, and x, 1, 1, 2, respectively. And, well, where's that coming from? Where's that coming from is, this was w minus 1. So we want to show that those guys are orthogonal direct sum for w minus 1. So, and that x, 1, 0, 2, orthogonal direct sum of x, 1, 1, 2 is equal to w minus 1. Which by the way, is Rx 1, 1. Okay, so, yes, Nate.
What did the theta 1, 0, theta 1, 1 look like? You said the bar system.
Well, they are the Walsh functions. That's exactly what they are. This is the amazing thing. And I'm not going to do those details tonight, but I will do
Oh,
them.
that like a picture.
Yeah, Walsh functions look, I mean, they're step functions. Things like that. But they don't arise in the, I'm going to do a lot of them. But for the Haar system, they're the Walsh functions. For other systems, you can imagine there's a source of exercises here and computer exercises. It's quite interesting.
Now you get the gray codes out of this somehow?
The what?
The gray codes?
Oh, I don't know.
Okay.
I don't know.
That's the ordering where you just change one bit as you're going through them. 1, 2. It's an order. It's a binary ordering, only changing one bit, and I seem to recall the Walsh functions can be defined using gray codes.
This is a Benedetto, I don't know.
Okay.
Okay, but let's put all this together in one ugly, it's not ugly, but it's one sort of package. So I guess we can, using the previous notation, we can make a theorem, but it's just summarizing what I've been saying. That when we're assume MRA, then each element X, R, M of the tree. Now, here M, I'm just counting from left to right. So this is, but this would be represented by some zeros and ones the way I've been making trees. each element XRM of the tree is a closed linear subspace of V0, right? Further, XRM is determined, R bigger than or equal to 1, is determined, defined by the function square root of 2 to the r, and this gives a formula for it, and then for the higher case, it comes out to be the Walsh functions, where we have theta hat epsilon 1 comma up to epsilon r 2 to the r gamma, and we have that pesky phi hat of gamma right here. But then we're going to have h epsilon 1 of gamma, h epsilon 2 of 2 gamma, all the way down to and I have a typo here which I will not be able to figure out standing in front of you right now, but h epsilon r, I'm going up to r, and I'm going to go, oh no, it's okay, 2 to the r minus 1 of gamma. Okay, so these are all genuine functions. This is a function on the real line. These are all one periodic functions, and we're looking at them scaled. And so we get a function on the real line, and we take its inverse transform to form our function theta, and that guy is the guy that's going to be how we get the span of the tree element graph. So let me finish it off to be careful. Where M is equal to the sum J equals 1 to R, epsilon J to the 2, J minus 1, where epsilon J is in 0, 1. And so it's defined by the function in the sense that I'm going to erase this, yes? In the sense that x mr is equal to the closed linear span of 1 over the square root of 2 to the r. We've got our function, so theta epsilon 1 epsilon r of t over 2 to the r minus n, where n is in z. Okay, that's what the tree, those are the functions in the tree. And not only that, and these guys here, and form an orthonormal basis for XRM, and even more, and V0 is the orthogonal direct sum of X, R, M, where M goes from 0 up to 2 to the R minus 1. So I think it's sort of amazing. One thing that I didn't say but it's basically what we have is for any fixed level R, we've got 2 to the R nodes, right? We get these Christmas lights. But we've got them at every level. Going to be at level, whatever level this is, there are 2 to that level. And so what I just said here is that the direct sum of all these trees forms a orthonormal basis for V0. But, and I did some nonlinear work on this matter with the woman student, that's relevant, because I asked her, is it okay to call this a hemline? She laughed at me. She thought I was very old-fashioned, Frieda, asking her permission on that. I guess I'm not saying anything risque, but you can have different hemlines to give orthonormal bases. I mean, they all have to come from the same node. You can't skip anything above it. So you can have a hemline like this, I guess. That sort of thing. And all the nodes on that hemline would form an orthonormal basis. So if you're interested in orthonormal bases, we have an infinite machine here. But the Walsh functions have tremendous other applications where, I mean, this is a generalization of Walsh functions. And next time, I'm going to stop now. I think I gave you a nice word tonight, even though the class was a little bit short. And Waldron saying, that's your opinion. I might have a different opinion, Professor. Next time I'm going to look at something. I'm going to start off with a general definition of wavelet packets. I haven't actually defined it yet. I'm just showing how to fill in a tree right now. So I'm actually define something called wavelet packets. And then we will look at the special case of the highs to get the Walshes, and we'll do a lot of other specialization. There's a lot of activity in the subject. Yes, sir.
If I understood Miss King correctly, she co-authored a paper with you.
Who's that?
Miss King, I forgot her first name.
Oh, Emily King.
Emily, yes. I think she said she co-authored a paper with you. It was like a machine, essentially, for just generating all kinds of orthonormal bases. Does that sound familiar?
Well, we only have one paper, so yeah.
Okay. Was that this or something
No,
else?
no.
Something else.
No, this was years ago. This was back in 1990. I did this.
Okay.
Okay. If you didn't enjoy it tonight, enjoy it. Have a nice bottle of Coke or something, and enjoy the pleasures of this